Okay, so happy to be here to speak with you this morning. I'm going to describe the Far Infrared Enhanced Survey Spectrometer. We call it FIRESS, which is led here at JPL, but with help from the folks at Goddard. Okay, so the concept for FIRESS, as Margaret mentioned, is full band spectroscopy that's sensitive, and this shows just some example modeled spectra with FIRESS. So it covers the 24 to 235 micron range. So that's a log scale there in wavelength. And on the top is a high resolution spectrum. And I'll say a little bit more about that toward the end of the presentation here. The other three, which have the colors, are the low resolution mode. And you see the four colors are the four bands of FIRESS, which are spaced logarithmically across this full range. Okay, so let's see here if I can advance. Yeah, so just looking a little more closely at those four bands. So let's see. First, I guess look at can you see my cursor? If you look at this portion, I'm looking at the upper right figure, the lower portion of that just shows one of the modules for the grading. And it's basically just a slit-fed spectrometer with a grading and then an array here in the lower right which has 84 spectral pixels. So this horizontal direction is the spectral direction, and then 24 spatial. And we do that with two detector chips. And that's important because you'll see how the slits map onto the sky in just a minute. So every one of each of the four FIRESS bands has this architecture. And they're the same size pixel. So the arrays are all going to look pretty much the same if you just look at them, with your naked eye. Okay, so here's a table with the four bands. So starting at 24 to 43, et cetera, up to 235. So these are an equal geometric spacing. Let's see, they all have a resolving power around 100. It varies across the band, but it's around 100 in this low resolution mode. And here you have the pixels at the bottom, the pixel sizes on the sky. So the pixel sizes, of course, grow with wavelength. And with the exception of bands 1 and 2, which have the same size pixel, for various reasons having to do with, well, primarily for cost savings, but also because we're less concerned about angular resolution at the very shortest wavelengths and more concerned about sensitivity. So this is, if you've used the Spitzer infrared spectrograph, in particular the low res mode, this is very similar to that. It has a little bit higher resolving power than the low res mode, but it's very similar in concept to those two low res modules on Spitzer. Okay, so now looking a little bit more about how these bands couple to the sky. So this figure in the middle shows the slits on the sky. Don't worry about the gray circle that says FTM for now. Let's just look at the slits. So there are four bands. So the orange is band 4, and this gray-green color here is band 2. And then over here on the right, you have bands 3 and band 1. So what we've done here is overlapped bands 2 and 4 in one place, and then bands 1 and 3, of course, subject to the fact that they have different pixel sizes, right? But what this means is that a given source can be positioned to couple to band 4 and band 2 simultaneously, or band 3 and band 1 simultaneously. So you get two for a given point source, let's say a distant galaxy that you're interested in, or a protoplanetary disk. You get two of the four bands at once, and two observations are required for the full spectrum that you saw in the figure. Now, for observing low resolution in the low res mode, for just getting the grading mode spectra, we'll be chopping the source back and forth. And so that's what you see here in the right side figure. So the blue and the red are example positions where you can put the source and light up different spectral rows in the spectrometer. So remember, the spectral direction is horizontal here, and this along the slit, we call that the spatial direction. And because there's this staggering of the spectral coordinate with the pixels, we get nice oversampled spectra if we observe the source in both this position and then in this position, for example. And there's some further alignment to ensure that this can be done for both of the two bands that are being observed at the same time. So we've thought a lot about how we can do this. Um, let's see. I think that's pretty much, yeah. Okay, so sensitivity. So what you see here is the sensitivity to an unresolved spectral line. So such as, a neon line in a Redshift 3 galaxy, for example. So this is again the full range. Now what we show here is the required sensitivity. This is not the instrument model. We have an instrument model, but this is what we recommend for developing the geo cases. And we'll of course be refining the instrument model as the formulation of the mission proceeds, and we'll have updated numbers. But for now, this is what we'll be using for the next, say, at least year or two, for the purposes of developing the geo cases. So this scales in the usual way. If you want to go deeper, you require 1 over the square root of the depth in time. Um, and this is what's in the exposure time calculator, this basic equation. So when you plug in the exposure time calculator for the FIRESS low res mode, it will execute this equation for you, basically. It's pretty straightforward. I think the other point, oh yes, just a reminder that either 1 and 3, so here and here, or 2 and 4 simultaneously. So you have to double the amount of time for a full band spectrum. So this low-res base spectrometer is also capable of mapping. And as Margaret showed, that's one of the things we're very excited about for PRIMA, is the mapping speed of PRIMA and of both instruments, really. And so this is a plot of that. And actually, this is the same figure that Margaret showed, cast in a slightly different light. This is the time to survey 100 square arc minutes to a depth of 3 × 10⁻19 watts per meter squared in a line in a source, right? So you can map, you can recover sources and spectral lines in those sources with the spectrometer, and that also, of course, has a straightforward scaling, where the depth scales as the square root of time, right? So you square the depth ratio to get the time required. And that's also all in the exposure time calculator on the web, but it's just this basic math, okay? I think I should point out, for those of you that use James Webb, this particular plot is perhaps a little bit unfair in the sense that this is for the 100 square arc minute survey to this depth, for which James Webb is essentially overhead limited. So for very deep observations, Webb can do much better. So just be aware that we're not trying to be dishonest here, but for this particular measurement, so for wider fields, PRIMA is really quite capable. It's very agile. Okay, so let's see. Let me go back and let's look at this for a second. So that's the low res mode. Now we also have a high resolution mode, as Margaret alluded to. And so now look at this gray circle here. This is the field of view of the high resolution mode. And the way it works is that it's engaged when we want to use it, and it intercepts the light that's inbound from the telescope to the grading modules, processes it, and then returns it into the same optical path to be fed through the slits and detected with the grading spectrometer. Okay, so the grading is used as the detection system for the FTS. I think the only point of this slide is just that the path length that is provided in the interferometer is what determines the resolving power available. And that number is 4,400 at 112 microns, okay? But it scales as 1 over lambda because it's the path length in units of wavelength that sets the resolving power. Okay, so this 4,400 is what is required to extract our hydrogen deuteride transition from the continuum in protoplanetary disks. But this system, of course, operates over all 4 bands and can be used for any number of experiments. But just to show you how this works, here's an example spectrum. Well, this is a modeled spectrum of a disk that covers this almost our full range here. You see just a rich spectrum, mostly water transitions in here, but there are other things as well. Atomic oxygen fine structure, for example, and of course the hydrogen deuteride transition. In this lower figure, you see a simulation of actually building the building this spectrum from the detector measurements up. And so I just want to show that briefly because people don't perhaps appreciate how this FTS plus grading works. And the way to think about it is that after you send the light through the FTS, each of these channels is like a bandpass filter for the FTS, and each of them measures its own spectrum. And then you simply co-add those spectra, those little spectra, optimally to generate this final spectra. And if you zoom in on that, you see it's quite sensitive. So this is a real simulation with real detector noise, letting the light through onto each detector, running the phase delay mechanism, and extracting the spectrum. So we're pretty excited about this. I think it's going to work very well. The reason for using the grading as the back end is the same reason that well, it's the same reason that you have more sensitive detection with the grading spectrometer in general. You reduce the photon noise in the detector by reducing the bandwidth on the detector. So that works with the FTS. So unlike Spire, which had a broadband on each detector, you can still get a spectrum, but this implementation is much more sensitive. And that's a factor that we gain in addition to the cold telescope lower background. Okay, so there's some more details on this in the JADIS paper that we have coming out on FIRESS, or it's in review, I should say, for our PRIMA special edition of JADIS, so you can learn more about this. Okay, so sensitivity in the high-res mode here, because we're going to be looking at bright sources in many cases, and we have to keep track of the source photon noise. And so there's a prescription in the ETC for you to put in the flux of the source, the continuum flux in Janskys, and you'll get the sensitivity out. And of course, a Jansky at 25 microns is more photon noise than a Jansky at 200 microns. So you have to put in the wavelength that you're interested in, the flux at that wavelength, the continuum flux at that wavelength, and then the line sensitivity that you want to reach in that source, and you'll get the time required. But this just shows you how that, as the sources become brighter, you have this square root of flux penalty from the sources themselves. Many of our disks will be in the range of 1 to a couple Janskys, for example, right? So this is important for us. Okay, I think that's all. Oh yes, again for the in high res mode also, you can only do one of the two pairs of bands at a time. So either bands 1 and 3 or 2 and 4. So for the full spectrum, you would need 2 measurements. If you just wanted to do HD, you in principle you could make me just measure 1. If you could do science with, say, this band 3 and band 1, and that's all you need, then you wouldn't need to observe the whole spectrum. Okay, happy to take questions. I'm not sure who's, I see a hand raised. Let's see.
Yeah, Margaret, go ahead.
Yeah, no, I was just wondering, just for clarification. So for the FTS modes, you say you have two, you have to take the measurement twice. But like the low resolution FIRESS mode that you actually do the nod pointing, is that the same for FTS?
No. Yeah, that's a good question. So a very good question. So let's see, maybe I can share again here if I'm smaller. So for the FTS, you simply position the source in the on one of the pixels and then use the FTS itself to modulate. You do not require chopping. We need to chop for the low res mode because you have to have some form of modulation, but the FTS provides that, right? So if we come back, so for the FTS, you just pick whichever of these rows. Well, okay, it has to be within the FTS field of view. Pick whichever of the pixels, whichever of the rows you like the best. Maybe there's a little bit better performance at 112 microns, and that's the hardest thing you're trying to do with your spectrum. You would select that would be in bands 1 and 3. You would select whichever position along this slit is best, right? And that may be important because our arrays will likely not have 100% yield. So there will be some selection of optimal positions. The other point to make, since you asked the question, is There is some spatial multiplexing. I know some folks have asked about this. You could call it mapping, but when you observe with the FTS, you get all of these, all of this, the intersection of the FTM field of view and these slits at the same time. So you are getting some multiplexing, of course, very useful for subtracting background, for example, in crowded fields. But you could build up a map with this as well if you desired, and particularly for bright areas.
Thank you.
Yeah.